Welcome back. It's good to see you here again for Related Rates, where we wrap up Chapter 2. I'm going to do this in two parts perhaps, so look for a second possible video looking at a couple more examples that you might quite often see. So the objectives, look at related variables and then solve related rate problems. And it all goes back to implicit differentiation, frankly. And this sometimes is wrapped into implicit differentiation and made it a one section. We're taking it in two because that's the way your book does, and I agree with it. So here we go. Related variables. Has nothing to do with your brother-in-law or your mother-in-law or anything like that. Had to get that out of my system. So we're going to talk about problems involving variables that are changing with respect to time. So we're going to be differentiating with respect to time and implicitly as well, as you'll see. So here's an example. X and Y are related by this simple equation, or at least it should be simple. If Y changes, X changes. If X changes, Y changes. And there's a good chance that if one changes, the other one will change in a similar way, but not always. So here's an example with that function, y equals 2x. Differentiate, and you can see how the rates of change are related to each other. They aren't distinct from each other. You can see that y has values twice the value of x, and the rate of change is always twice the rate of change. That's pretty simple. Not always quite the same, but you get the point. So we'll look at one that's a little bit different. Here, x and y are differentiable functions of t. That means they're continuous and we can differentiate them. They're related. Y equals x squared plus 3, as you can see. So when you differentiate it, or excuse me, before that, here's a sample type of problem. Let me check my pen, make sure it's working good. There we go. So here's a set of variables. And what we're talking about is dy dx equals 2. That means that's how x is changing as time goes by. And we're interested in what is happening at x equals 1. So first of all, we're going to find dy dt. We're going to be differentiating both y and x with respect to time. And find it when x equals 1. Now, in the previous example where y equals 2x, the derivative, or the dy dt, was always 2. Here, not quite the same. So here we go. We use chain rule, of course. Even if we don't use the chain rule, think about the possibility that you might need to use the chain rule. I can't say that too much, apparently. So we'll differentiate both sides with respect to t. Notice that. It's not with respect to x. That's what we did in the past. We don't have to be constrained by differentiating with respect to x all the time. So here we go. There's dy dt, and differentiating the other one, if you want to look back here a second, we're differentiating x squared plus 3, and there's our answer on the right hand side. This is the derivative of x squared with respect to t. And the dx dt, because we're using the chain rule, and on both sides really, because we have the derivative being 1 here, but since y isn't t, then we have to throw in the dy dt. Now, what we're interested in is when x equals 1 and dx dt is 2, what is dy dt? All we need to do is put in what we've been given, the 1 for x, and the 2 for dx dt. There in red are our two insertions, a simple multiplication, and our dy dt is 4. That's how y is changing with respect to time. So with that startup, here's a related rate problem for you. Let's suppose we drop a pebble into some water. What happens? We get these concentric circles rippling outward from where the pebble hit the water. As time goes by, these circles gravitate outward. I shouldn't say gravitate, but they move outward. We also know that the radius is increasing. That's the distance from here to one of the ripples is increasing at 1 foot per second. What does that mean? Well, you have to get used to this. dr dt is 1 foot per second. We want to know when the radius is 4 feet, at what rate is the total area changing? Okay, so now we're talking about area. Remember, these are concentric circles, so area and radius are connected by this equation giving us the area of a circle. You're familiar with this, pi r squared. These are the two variables of interest, the area and the radius. So we're going to differentiate both sides of this equation with respect to time. We're going to just stick with time most of the way. So there's our equation. There's our start. The rate of change of the radius, dr dt, is this 1 foot per second. So our given rate is 1, and we're interested in how is the area changing when the radius gets 4 feet in, 4 feet from the center. So we'll take the derivative of that equation with respect to time, and we're going to find out dA dt when r equals 4. Notice what we've done here. Here is our equation that's going to tie all of those variables together. These are the pieces we know, and that's what we're looking for. You might write those down as steps, which will go into your head eventually, but here's the equation we're going to be using, the reference equation. Here are the pieces we have given or that we know, and this is what we're looking for. There's our original equation. Take the derivative with respect to time. You might even want to write this out. It's not a bad idea. Maybe you want to write it like this. Pi r squared prime like that. That's all up to you. Whatever works for you. I would suggest perhaps writing it like this to begin with and develop your own style. There's the derivatives. We've got dA dt, and we've got the derivative on the right hand side as well. Now it's time to put those given pieces together. We're interested in what's happening when the radius gets as big as 4 feet, and we already know the way the radius is increasing is 1 foot per second. Just put those numbers in for those variables. And what we get is 8 pi. Now what we need to remember is we're finding out how the area is changing with respect to time. So this isn't just 8 pi. It's 8 pi square feet because it's area per second. Just put those numbers in Don't forget the units. And then how do you write it up? When the radius is 4 feet and the area is changing at the rate of 8 pi square feet per second. In reality, we probably would multiply that out and get 24 point something square feet per second, but we're talking about an exact value, so it'd be 8 pi square feet per second. Okay, now another thing you might notice is as that pebble hits the water and you start getting those circles going out and out and out, and the area is becoming bigger and bigger and bigger. See what's happening. First of all, with the radius, every second it's 1 foot further away from the center, going from 1, 2, 3, 4, 1 notch each time. The area, though, doesn't go by 1 piece per second like the radius did. This one goes 2 pi, 4 pi, 6 pi. It doesn't go up by the same amount each time. How can you tell? Well, we're not going by 1 piece at a time. This isn't going that plus 1. No, it's going up by 2 pi, another 2 pi, another 8 pi, and that's how the area is changing. Now, here are 4 steps you can use to follow. Figure out what quantities are given, what you have to find out. Make a picture and label the picture. Label the pieces in the picture. Write the equation that puts all those things into one nice package. Then use the chain rule to differentiate both sides with respect to time. Remember, it'll be d something dt for these. And last of all, put all the ones that you're looking for on the left side, all the rest on the right side. Solve for the required rate of change. Here's another one, for example. This would be one of those that ties things together. Volume related to the radius. That would be like if you were blowing up a balloon, a circular balloon, of course. And this would be the radius of the balloon at any one time and the volume associated with that. 4 pi over 3 times r cubed. You might almost memorize this. We're going to use the volume of a sphere several times, I'm sure, in examples and exercises in the book. Now, here are some things that you might keep in mind. Just read through these. So you might hit a pause between each one of these and give these a few seconds of thinking. The velocity of a car after traveling for 1 hour at 50 miles per hour. The 1 hour is a time, 50 miles per hour is a rate. So you've got x is distance traveled, that's part of the model, and dx dt is 50 miles per hour when t equals 1. All those pieces. And there's the model. Another one. Water is being pumped into a swimming pool. You can get a picture of that, as well as the car. It's being pumped. And of course, the pump is constant at the rate at which it puts water into the pool. 10 cubic feet per minute. The volume is changing, and here's how it's changing. Population of bacteria, and they're increasing at 2,000 per hour. I hope this isn't something that's making us sick. This is how many are in the population, and that's how they're increasing. So these are just to get your mind thinking about what kinds of variables, what kinds of relations, what kinds of givens and models that you can have. Revenue is increasing at the rate of $4,000 per month. R is the revenue, DRDT is the rate of the increase. Profit, of course, revenue and profit, good business examples. Profits is decreasing. Well, that doesn't sound real good if we're the business owner, but this is just an example. It's decreasing at $2,500 per day. P represents the profit, so you'd have something to do with profit for your given mathematical statement. And dP/dt is what you'd be working with. That's the negative 2,500 because it's decreasing, and it's a rate. Next, let's get to a real example here, at least in this session. So here's the weekly demand function. Remember, the demand function is sort of weird because it starts with P equals, and that's the unit price in dollars in this case. Could be in euros or something else, so make sure in your answer you put down dollars as opposed to euros or rubles or something else. And X is the number produced each week as opposed to being sold. We want the rate of change of the revenue. So what does that mean right away? We're talking about DRDT. In dollars, so it'd be dollars per what? Well, up here it talks about weeks, so it'd be dollars per week. And when the weekly production is 2,000 units, that would be the X, because we're talking about number of units in a week. And we've got a second question, but we're going to take care of that after we get the first one solved. Because once we get the first one, the rate of change of the revenue, then we can compare it to the 20,000 and answer that question. So here we go. Production is increasing at 2,000 per week. So this is a positive 2,000 for dx dt. Remember dt. So here's our problem. Here's our given rate. That's given in the question. Here is what we're looking for. And to get that, you need some kind of an equation that puts R and X together in the same equation. Well, here's our equation. We had it in terms of P, but that isn't good enough. That's not the revenue. We need X times P. That's how much money we're going to make by selling it at this price for each one and selling that number of items or producing that number of items. And here was our price equation or our demand equation. Multiply that by X to get the revenue, and there is our equation or our formula. So you're going to differentiate it. It's over time. We're going to be working with time almost exclusively. So you're looking for dr dt. There's your setup. So you can take it one piece at a time. Do your differentiation. On the left side, you get just dr dt. Good. That's what we're looking for. All we have to do is put the right numbers in on the right-hand side. We'll be set. X is 2,000. Put that in here. dx dt is 200. Put that in here. That's it. Just put those numbers in. The revenue is increasing at $19,200 per week. And there's our first answer. We got a second one though. We were supposed to compare it to 20,000. It isn't greater than 20,000 per week. So there is our answer. And that's also the end of this video. I'll see you in the next one. And hopefully I'll do that this afternoon. Take care of yourself, and I'll see you on Monday morning. Bring some questions. Until then, take care.